Okay, welcome back to Mr. Hassan's Maths channel. I am now going to go through the Solomon G question number, what's happened here? I'm supposed to say in one second. Question, Solomon G paper for Mechanics 1. It's question number 2 for my end of topic worksheet on my M1 collection. End of topic worksheet number 4, connected particles. And this question here starts off about a car of mass 1200 kilograms which tows a trailer of mass 800 kilograms along a straight level road, it's horizontal road, by means of a rigid tow bar. It's not a rope, it's not a string, it's a rigid tow bar. It's a difference. The resistances to motion of the car and the trailer are proportional to their masses. Given that the car experiences a resistance to motion of 300 newtons, find the resistance to motion which the trailer experiences. Okay. So here we're told that the resistances to motion are proportional to their masses. Okay, so let's see the ratio of their masses. Okay, you've got the trailer and the car. So you've got car and trailer. And you've got trailer. Okay, so the car experiences a resistance to motion of 300 newtons and the trailer experiences a resistance to motion of x newtons. I have to find that. The car has a mass of 1200 kilograms and the trailer has a mass of 800 kilograms. Okay, so you can say here from this that the ratio of the masses is going to be 12 over 8, which is 3 to 2. So that's 3 to 2. So you're going to have 300 to x. So we can say x is going to be 2 times 300 over 3, which is 200 newtons. So we can say that the trailer has a resistance to motion of 200 newtons. Okay, so there's the answer to part A. Okay, so it's just simple proportion here. Alright, so given that the engine of the car exerts a driving force of 3 kilonewtons, find the acceleration of the system and show that the tension in the tow bar is 1200 newtons. So what I need to do is make a clear diagram showing all the forces acting on this system. That's what I need to do. So what I'm going to do here now is I'm going to make a diagram. I'll try and do it neatly with this pencil, or my version of a pencil and a ruler. So you got a car. In fact, I won't even draw this road. You've got a car and you've got a trailer. So let's say this is the car and this is the trailer. Okay, I'll make a bit of space between them so we can. No, that's the car and that's the trailer. Alright. The car is pulling the trailer by means of a rope. Okay, by means of a rope. Okay, and we know that the car is mass 1200 kilograms. That's 1200 kilograms, and this has a mass of 800 kilograms. Okay, this is the car and this is the trailer. Okay, the car is pulling the trailer. Okay, the engine of the car exerts a driving force of 3 kilonewtons. So in this direction, the direction in which it's pulling the trailer in this direction here, there's a force acting of 3 kilonewtons, which is 3,000 newtons, pulling the whole system. All right, and you've got resistances to motion of the car and the trailer. Okay, so for the car it's 300 and for the trailer it's 200. So you've got 300 resistance here and 200 resistance here. So that's 200 newtons and that's 300 newtons. Okay, and we have what else? Okay, all right, so that's it basically. So of course we have the tension in the tow bar. So this is being pulled this way, and this is having an effect of slowing down the car as it's pulling it. So the tension in the tow bar is acting in this direction. This is the trailer, and this is the car. Okay, just to differentiate from that T. Now, what we have to do is find the acceleration of the whole system. As they are moving in the same straight line, and they are both, connected by this rigid tow bar. Okay, it's a rigid tow bar, so basically it's like it's inextensible. It doesn't stretch, doesn't bend or buckle. So the tension throughout the whole tow bar will be the same, and also the acceleration of anything attached to the tow bar will be the same. So I'm going to take it as one particle. So consider as one particle, as one big particle. Okay, so I can consider it as basically one particle, all right, with a mass of the sum of those, which is 2,000 kilograms. And I can consider the driving force acting this way is the same 3,000 which the car is exerting. But the resistances to motion together are going to be 500 newtons. Okay, and it's accelerating in this direction. And here, each of these accelerations for each of these two are the same. So one whole system is accelerating together. So I can use the fact that the resultant force is equal to the mass times the acceleration. So if I resolve my forces horizontally, I can say 3,000 minus 500 is equal to the mass, which is 2,000, times A. Okay, and then I can find what the acceleration is. Okay, so then I can say 3,000 minus 500 is 2,500 equals 2,000 A. Cancel out two of the zeros. So I have A equals 25 over 20, which is 5 over 4, which is 1.25 meters per second squared. So that's the acceleration of the whole system. 1.25 meters per second squared. Okay, and then it says show that the tension in the tow bar is 1,200 newtons. So now I know the acceleration in the system, so I can concentrate on just one part of the system. So for example, I can consider just the car, or I can consider just the trailer, and I can find the tension in the string because I know the acceleration now is 1.25 meters per second. So I know 1.25 meters per second squared is now the acceleration of the whole system. So if I consider, for example, just the trailer, okay, now the reason why I'm considering just the trailer is because there's less forces acting on it. Okay, just the trailer. Okay, then I'll be able to find the tension in the string because I have now everything except this. So I'm going to think about just what the forces acting on the trailer alone. All right, now some people will think, but what about this 3,000 newtons? Okay, what about the force here? What about the weight of this? Or what about the resistance to motion of this? All of those things are factored in its acceleration and in the tension in the string. If this force was greater, the tension in the string would be greater. Okay, so this tension is, all those things are factored in this acceleration and in this tension. Okay, so we don't have to think about the whole picture. If we're trying to find the tension in the string, we concentrate on one part of the system. Okay, I could even take in this part, which I'm going to show you, and see that we get the same answer. So here, the resultant force, if I just thinking about this trailer, is going to be T minus 200. And that's equal to the mass of just the trailer times its acceleration. So I'm going to say that considering just the trailer alone, I've got the resultant force equals the mass times acceleration. So the resultant force this time is going to be T minus, which we have to find the T, minus 200 equals the mass of the trailer being 800 times the acceleration, which we know is 1.25. So you have T equals 800 times 1.25 plus 200. So that will be the tension in the rope. So you have 800 times 1.25. You add to that the 200, and you end up with 1,200. So the tension in the rope is 1,200. Now I'm going to show you, just for the sake of showing that it doesn't matter which one you use. I could have used the car. The car, there's just an extra force acting, that's all. Again, I'm going to resolve in this direction like I did here, because that's the way everything's moving. I like to resolve in the direction of motion. So here I've got 3,000 minus, and I've got T, and I've got minus 300, because those are that force is acting to the right, so that's positive, and the resultant force is with these two forces now, and that's equal to the mass, which is 1,200 times the acceleration. So I got 3,000 minus 300, which is 2,700, okay, minus T equals 1,200 times 1.25. Okay, so let's see what that gives us. So we're going to have 1,200 times 1.25. That gives us 1,500. So I've got 2,700 minus T equals 1,500. Was that 1,500? Yes. So then I can say 2,700 minus 1,500 equals T. So T is equal to, so I've got this 2,700 minus that, and you can see we're going to get 1,200, exactly the same answer. Okay, this was more hassle because we had more forces to deal with, because you have the pulling force and the tension and the resistance. Here you have just the tension and the resistance, but they give us the same answer. I can concentrate just on the car alone, which I did there, or I could concentrate on just the trailer alone. If I concentrate on the car alone, okay, I get the same answer as if I concentrate on the trailer alone. Okay, just for the sake of showing, you don't have to do both of these, of course, just to show you that it doesn't matter which one you count on. So to find the acceleration in the whole system, I wanted to get rid of the tension, which is unknown, so I took it as one whole system, which you can do because they're moving both in the same straight line. And then once I found the acceleration of the whole system, every part of the system has that same acceleration because they're connected by a rigid tow bar, in which the acceleration is the same all the way through. Okay, so therefore we have the answer to part C. Now moving on to part D, it says, when the system has reached a speed of 24 meters per second, it continues at a constant speed, at this constant speed basically of 24 meters per second, until an electrical fault causes the engine of the car to switch off. The brakes are used to apply a constant retarding force until the system comes to rest. Given that the retarding force of the brakes has a magnitude of 1 kilonewtons, and assuming that the original resistances to motion of the car and the trailer remain constant, calculate the distance that the trailer travels during the braking period. Okay, so now there's going to be a change here. All right, the change is going to be the fact that this is going to go. All right, electrical fault occurs. This driving force is no longer applied. Right, there's no driving force. There's going to be a new force acting, which is the braking force. I'll just draw it like this. The braking force, which is 1,000 kilonewtons. That's a new force acting here. 1,000 one kilonewton, so 1,000 newtons braking force. Okay, and yeah, so that's the new force that's going to be applied to the system here. And also, what's going to change is this. You're no longer going to have a tension in the string. This is called a tow bar, right? So once the brakes are applied, the brakes are only acting on the car, not on the trailer. So what's going to happen if there was no tow bar here? For example, if it was a string, then, you know, it wouldn't be being pulled anymore, and this trailer would go straight into the back of the car. But we have a rigid tow bar. Okay, now this tow bar it doesn't bend nor buckle. So what's going to happen once the brakes are applied, you're no longer going to have a tension pulling the car, the car towards the trailer, and the trailer pulling the trailer being pulled towards the car, nor the car being pulled towards the trailer. There won't be that effect anymore. The force in the tow bar will act to keep them apart. So you're going to have the force acting outwards like this. This is now called a thrust, not a tension. So when it's a rigid tow bar, when the brakes are applied on this, and normally this would go smashing into the back of it. If they're connected with the tow bar, that won't happen because it's a rigid tow bar which does not bend nor buckle. So what's going to happen is you're going to have what's called a thrust acting outwards to keep them apart. Okay, so they're not being pulled towards each other, they're being pushed apart from each other. Okay, so that's what happens in that type of situation. Because there's no brakes on the trailer, there's brakes only on the car. So the tow bar is what's going to stop the trailer from hitting the car. All right, so the thrust in that tow bar acting outwards to prevent them from smashing into each other. Okay, so now what I'm going to do is I'm going to consider this as one whole system. Okay, they say that the braking force is constant and the resistance to motion are constant throughout the whole time. So let me see the forces acting on this as it is braking. So I'll take this one whole particle as I did before. So its mass is 2,000 kilograms. And I'll take the total resistances to motion, which is going to be the braking force and those two, the total forces that are slowing it down basically are going to be 1,000 newtons, which is it's not the thrust, it's basically the braking force. Okay, and plus the two resistance to motion 500, so that's 200 plus 300, 500 plus 1,000, that's 1,500 newtons acting to slow it down. There's no driving force anymore. Okay, that's gone. All right, so these are the only forces acting upon this, and it's accelerating. Okay, it's decelerating, of course, but it's still moving in this direction. Okay, until it comes to rest. So I'm going to take this as positive. I'm going to look at the resultant force. I know that the resultant force is equal to the mass times acceleration. Here the resultant force is minus 1,500 because I'm taking the right as positive, and that's equal to the total mass, which is 2,000 times the acceleration, which I have to find. The acceleration in this system is no longer the same as the acceleration in the first situation because the forces acting on it have changed. So the acceleration will also be changed. I can't use the acceleration from the first three parts of the question for this part of the question because the forces acting on the system have changed, which will cause acceleration to change. So we can't use that same acceleration. Very, very important point. So therefore the acceleration is minus 1,500 over 2,000, which is like minus 15 over 20, which is minus 3 over 4. Minus 3 over 4, that's the acceleration, so we can say minus 0.75 meters per second squared. So it's a negative acceleration. Now, we want to find the distance it travels during the braking period. Now, they've said assuming all the forces remain constant throughout the motion of the car, that means the acceleration will remain constant. So we can use the equations of motion related to constant acceleration. So we have to find S. We know the initial speed, as I said, at the point when the car has reached this speed, that's when the engine switches off. So it's going at 24 meters per second at that point when the engine switches off. So that's its initial speed in this new situation. Its final speed is 0 because we've got to find the total distance it moves until it comes to rest, until the final velocity is 0. The acceleration is what we just found, minus 0.75. I don't think we need the t. We can see we've got S, U, V, and A. So we can use V squared equals U squared plus 2AS. So we've got 0 equals 24 squared plus 2 times negative 0.75 times S. So we got 0 equals 24 squared. Let's see what that is, 1 second. So we have 24 squared, which gives us 576. So you have 576 minus 1.5s. So therefore we can say 1.5s is equal to 576. So s is 576 divided by 1.5. So that's the distance it travels. So this divided by 1.5, that gives us 384 meters. So the distance it travels is 384 meters before it comes to rest. Okay, so now part E says find the magnitude and direction of the force exerted by the tow bar on the car. So we mentioned here already that there's a thrust that's keeping them apart. So the thrust is acting towards the car. It's towards the direction of the car. Okay, in the same direction that the car is moving. Okay, just before it comes to rest. So now what we can do here is we can say that let's look at the resultant force acting on the car. So consider the car. I mean, in fact, we could actually look at just we could just look at the trailer. Okay, and we could look at the car. Whoops, we can look at the trailer or the car. Okay, the trailer and the car both have the same thrust acting on them. So I could look at the trailer or I could look at the car to find the value of T, but looking at the car, we'll say the thrust is going to be acting towards the car, and the trailer, the thrust will be acting towards the trailer to keep them apart. So in fact, I'm going to consider the trailer because, as we saw, it's less forces, less hassle. Okay, so I'm going to consider the trailer to find what the value of the thrust in the tow bar is. So I'm going to have, if I look at the trailer, the forces acting on the trailer are both acting towards the left. Now the trailer is moving this way. Okay, so I'll take that as positive. So I can see the forces acting on it are minus 200 and minus T. So minus 200 minus T, and that's equal to the mass, which is 800, times acceleration, which we know is minus 0.75. Because now that's the new acceleration of the system. So we have minus 200 minus T equals 800 times minus 0.75. So we're going to have 800 multiplied by negative 0.75. That gives you minus 600. So you have minus 200 minus T equals minus 600. So you'll have minus 200 plus 600 equals T. So T is going to be equal to 400 newtons. So we can say that the direction of the force exerted by the tow bar on the, so the magnitude of the force, the magnitude is equal to 400 newtons, and the direction is towards the car. The direction is towards the car. Okay, in the same direction as the car is moving. Okay, because it's keeping them apart from each other. So the thrust is going to be acting in relation to the car towards the car. Okay, the thrust that's acting the tow bar towards the trailer will act towards the trailer. Here it's going to act towards the car because it's pushing them apart from each other. Okay, so there's the answer to question number part D. Then it says comment on the assumption that the original resistances to motion of the car and the trailer remain constant throughout the motion. Okay, so that was an assumption that we made to make our calculations easier because we can use SUVAT. But in reality, the resistances to motion change with the speed. Okay, so you can say in reality, the resistances to motion, the resistance to motion would change, okay, as the speed changes. So for example, the air resistance changes, it becomes, air resistance becomes greater when the speed is greater, less when the speed is less. So that's, you know, an assumption which in reality wouldn't really be true. It's just an assumption we made so we can use SUVAT equations and simplify the situation. That's what modeling assumptions are for, things that you can use to make make life a bit easier for you in your calculations. So there we have the answer to question number 2 from my end of topic worksheet, and number 7, I think it was it 7, from the Solomon paper, Solomon G of Mechanics M1. Other questions from this Solomon G paper for M1 you can find when I answer them in the playlist that should appear in this area. Other questions about this topic of connected particles you can find in the playlist that should appear down here. You can find other questions from this end of topic worksheet on connected particles in the playlist down here. You can subscribe to my channel from this area, and at the top of the page there will be a card taking you to an M1 past paper you might want to watch. Thank you for watching and see you soon.